Hi, this is part 2 of the BGA Cloud Flying Endorsement and SFCL Sailplane Cloud Flying Rating package. And in this part, we're going to be talking about the theoretical training package, so the theoretical knowledge that you need in order to get this qualification. In the introduction last time, we talked a bit about regulations. This is going to be the theoretical training. And in part 3, we'll talk about flight training. The syllabus that we'll be working to is based on the published SFCL syllabus, and the topics you can see here. We've got human factors and body limitations, principles of flight and aircraft performance, aircraft instrumentation, navigation, communications, and hazards and emergency procedures. We put a little bit about the rules and common sense in at the end. You can expect whichever instructor you're flying with to check your knowledge on this stuff, so do go through it a couple of times so you're familiar with the material. Let's start then with human factors and body limitations. We've spent a lifetime trusting our 3 key orientation senses. So we have visual senses from the eyes, we've got the inner ear which helps us with motion, and we've got the proprioceptive senses, so that's our skin, our muscles and our joints. The eyes confirm orientation. The inner ear tells us about changes in rate of rotation. And the problem is that if we're flying in the middle of a cloud, we don't have any visual reference for the eyes. And we'll discover what the limitations of the inner ear are when we talk about it in a moment. You can see here where we're getting those signals from. The problem is these can all be very misleading. We'll talk a bit about acceleration and tilt and the leans, which are features that come from the inner ear. And we also find it quite easy to deny what we're actually experiencing, and we can fix on particular instruments. So let's have a look at some of those things. The message is going to be that we must learn to trust the instruments. We have our own artificial horizon in our head, but actually it's not very good, and that's a bit of a problem. It's the inner ear, and in the inner ear are 3 semicircular canals, each at right angles to each other. In the semicircular canals, you can see here, are little hairs which stick up with little chalk balls on top of them. And these do 2 things. One is they give us an absolute reference of which way is up. Because if we're at an angle, the chalk balls weigh the hairs down, and that tells us that we're not vertical. That works fine when we're standing on the planet Earth, but it's useless in an aeroplane because you can't tell from the direction of acceleration which way is up. The second thing that they do is if we start rotating our head in the plane of one of these semicircular canals, the fluid takes a while to catch up. So we can measure the acceleration, that rotational acceleration, by the way that the hairs move in the semicircular canal. And that's okay, but it's got 2 problems. One is that we can't detect small accelerations. There's what's called hysteresis. And the second problem is that the 3 semicircular canals are connected. So if we rotate in one plane, which starts fluid moving in that plane, and also rotate in the second plane, which starts fluid rotating in the plane, the semicircular canal in that plane, then what happens is that those 2 fluid flows couple and we get fluid moving in the third plane, which we're not rotating in. So how does that, what does that mean? What happens? Well, that last thing causes us to feel like we're tumbling. So imagine that we're turning in a glider, which we do frequently if we're thermaling. So we start fluid rotating in one plane, and then we move our head in a second plane, well, that might feel like we've just done a somersault. And I know somebody who unfortunately died because of just that phenomenon in an aeroplane. The problem of the semicircular canals only detecting acceleration over a small amount can lead to something we call the leans. So imagine we're flying along using an artificial horizon, keeping the wings level. And as we look for other things, we allow the left wing to drop very slowly to maybe 10 degrees wing down. Now it's been slow enough that our semicircular canals haven't detected the drop, but we look and we see that we're left wing low. So we move the stick and we pull the left wing up, and we do it fast enough that the semicircular canals detect that. So the wings are now level, but our body thinks that we're now 10 degrees right wing down. We go back to flying. Because the body thinks we're slightly right wing down, unconsciously we slowly allow the left wing to drop again. The body thinks it's bringing the wings level until we're, say, 10 degrees left wing down again. Oh, we notice it and roll right. So each time we do this roll right, what has happened is we've brought the wings back level, but the body has ratcheted up another 10 degrees of bank. So we can end up in a situation where the body thinks, our body and our mind think that we're in a 50, 60 degree bank turn, but our eyes using the artificial horizon are telling us that the wings are level. And it's very, very disconcerting. You can sit there with the sweat pouring off you as you fight what your mind is telling you is happening and keep the wings level by looking at the artificial horizon and the other instruments. The third way we can get errors because of the imperfections in our own instrumentation is acceleration errors. We have the little hairs here, and they detect the sense of the vertical by being vertical, and if we lean our head back, for example, they'll bend because they're now at an angle and the chalkballs are pulling them down. But the same happens if we accelerate. So this applies to aircraft taking off from aircraft carriers as they accelerate quickly. The hairs are moved backwards and it feels like a pitch up. So the natural reaction is to move the stick forward to stop the nose from pitching up, and that can be the wrong thing to do. It's the wrong thing to do on aircraft carriers. Airliners have crashed because of it in a go around, and I can think of a very good example of a situation where we do exactly that in gliders, which is winch launches. But we're normally looking quite hard out at the outside at that point, so we have that benefit. It's worth noting that our eyes are dominant. What we see tends to override our other senses. So if we've got a good horizon, a good external visual horizon, it's super. We can not worry about the other things too much. If we don't, it's a problem. And the last thing that can happen is motion sickness. And the motion sickness often comes because of the disconnect between what our inner ear is telling us is what has happened and what our eyes are telling us about what has happened. So the conclusion is we must learn to trust the instruments because our own instruments really aren't very good. One of the things we'll demonstrate when we fly is how long it takes to become quite disoriented if you go into cloud without a good attitude reference that you can use, a good instrument in other words. And I think the assumption is that an untrained pilot in 30 to 45 seconds will no longer be level and will be in danger of crashing. So in cloud, we have to trust the instruments. It's worth saying a little bit about hypoxia, because sometimes when we're instrument flying, it's because we've been flying in wave and we've got quite high. And hypoxia is quite a big issue if we're going to fly high. There are 4 stages of hypoxia: indifferent, compensatory, disturbance, and critical. The first stage, indifferent, really between 0 and 5,000 feet, is a stage where there aren't any significant effects observed in most people, most healthy people. Above 5,000 feet, though, we get to what's called the compensatory stage of hypoxia, and the effects start occurring. Night vision is affected, some particularly new task performance is affected, so we can't do new things as well as we would expect to be able to, but most functions are okay. Above that, we have the disturbance stage between a little over 11,000 feet and 18,000 feet. And at that stage, we're really getting quite short of oxygen. Breathing rates increase. We lose the ability to monitor ourselves and have good cognitive feedback. We have difficulty thinking, and there's a lot of variation between people. Some people can cope at higher altitudes than others. But this is quite dangerous, not least because we lose the ability to be rational about what's happened. Above that, above 18,000 feet or so, we're in danger of complete incapacitation with little warning. And it's worth understanding this and understanding that we need to be on oxygen if we're going to be at these higher levels, and we need to be aware of what the symptoms might be just in case something goes wrong. It's also the case that getting on oxygen very early helps avoid an oxygen debt before we get higher. Here are some signs of hypoxia that we might want to look out for. Breathlessness, hunger for air, excessive yawning, tiredness and fatigue, euphoria, a bit like being drunk, an impairment of performing a recently learned task, impairment of other tasks, and then an altered sensorium, things feel strange, right up to loss of consciousness. So, let's have a look at the principles of flight. So, aircraft performance, pitch, roll, and yaw. The airplanes that we fly, the gliders, are pretty stable in the short term if they're properly trimmed in pitch. They will diverge in the long term, so I mean they'll leave the attitude that we've got. And gliders aren't terribly stable with the air brakes closed, but they're much more stable with the air brakes deployed. So, but generally, if we have a trimmed glider, then not much happens in pitch very quickly. So our speed tends to stay the same, even if over a long period of tens of seconds it will diverge. So it's not the thing we're going to concentrate on. In roll, our gliders tend to be spirally unstable. So if we don't do anything, they will tend to gently increase the amount of roll and we'll end up in a spiral dive. And in yaw, generally they're pretty stable if we keep the wings level. So if we put a boot full of rudder on and then take our feet off, in general, it just comes off without any sort of phugoid. And we'll look at these 3 things in the air. Things that can go wrong, a stall, generally unlikely unless we mishandle the glider, because our speed is stable. A spin, again, fairly unlikely unless we mishandle the glider, but a spiral dive is a quite likely scenario. So that's the one that we need to be careful about. How about the sailplane itself? Well, the first thing is it approved for cloud flying? That's going to be in the flight manual. You probably ought to know that. What's the maximum mass restrictions when you are cloud flying? And that's going to be driven by the need for the air brakes to be speed limiting in a 45-degree dive. Otherwise, that requirement is normally 30 degrees. So it needs to be able to dive steeper with a limiting speed with the air brakes open if you're going to go into cloud. And one of the ways that they might achieve that is to say don't fly in cloud with water. So you need to understand that. There's some extra equipment you might need over day VFR flying. You might need a turn and slip with a slip ball, a variometer, radio, a clock, and it might recommend an artificial horizon or attitude indicator. Now, our strong recommendation is that you don't try cloud flying with a turn and slip, certainly not in a modern slippery glider, but you have at least one attitude indicator. Your glide angle is going to be probably worse than 7:1 at your maximum permitted cloud flying weight when your air brakes are fully extended, so you need to understand that. And you've got two pitons. You might think about which one to use, and the one that ices up first is probably the best one to use, and then you've got a warning. Have you got a backup battery? What happens if you run out of power? That's not, in the middle of a cloud is not the time to do that. And perhaps be a little concerned about extreme cold in wave and your gel coat. Very, very cold conditions, particularly if you warm up quickly as you descend, can cause damage to the gel coat. Now let's have a look at aircraft instrumentation. Let's talk a little bit about instrument performance. There are basically two types of instrument we use when we're cloud flying. The first is a control instrument. It's going to tell the pilot what's going to happen next. And the second is a performance instrument. It tells the pilot what happened recently. There's only one control instrument, and that's the attitude indicator or artificial horizon. That tells you what the airplane is doing right now and therefore what is going to happen next. The performance instruments are pretty much everything else. The turn and slip, the airspeed indicator, altimeter, the compass, the variometer and the yaw string. They have some degree of lag in what is happening. Let's start with a turn and slip. You'll see this quite commonly in gliders, particularly older gliders. Quite a simple instrument. It's going to tell us our rate of turn and how much slip we have. So it looks like generally one of these two types of instrument. We have different rates of turn, a rate 1, a rate 2 or rate 3. A rate 1 turn is 2 minutes for 360 degrees. So that's 3 degrees per second, and at 60 knots that gives us a bank angle of 9 degrees. A rate 2 turn, twice that rate of turn, and that would be a bank angle of 18 degrees. And a rate 3 turn, we're going to be looking at about 33 degrees. Here's a little video showing the operation of a mechanical turn and slip.
With the cover removed, we can see the off flag linkage, the gyro motor stator, the gyro rotor, the power cords, the power connector and the gimbal. The operation of the slip indicator is completely independent of the gyro. The slip indicator is a ball inside a glass tube filled with some kind of damping fluid. The ball position is a resultant of gravity and centrifugal forces. In order to perform a coordinated turn, we have to keep the ball at the center of the slip indicator. The turn indicator incorporates a rate gyro, which means that the gimbal is restrained by a spring. The spring will return the gimbal to null position when the reason of deflection does not exist. The turn rate pointer is linked directly to the gimbal via motion reversing gear set, so any movement of the gimbal is translated to pointer movement. With the gyro powered and operating in normal speed, we will rotate the indicator around all three axes to see the reaction of the gyro in every case. So, as you can see here, turning the indicator around the longitudinal axis, nothing happens and the pointer remains centered or no turn indication. This movement corresponds to the airplane banking. If we move the indicator around the lateral axis, the gyro will not react again, as there is no any turn, and this movement corresponds to airplane pitch changing or climb and dive. But if we move the indicator around the vertical axis, which corresponds to airplane yaw or heading changing, the gyro reacts immediately, moving the pointer in proportion with the turn rate.
The artificial horizon or attitude indicator, these are a couple of mechanical ones, the one on the left being a little bit more modern than the one on the right, which is an old military one, I think. We'll have a look and see how the mechanical ones of these work in the next slide. And here's a video showing the operation of an artificial horizon.
And an outer gimbal. You guys have done that as well. You've looked at gimbals.
The gimbals, no, show them that.
Okay. And then an outer gimbal with 360. So you can barrel roll an aircraft. Can you notice that if the top of this rotor is facing the roof, no matter what I do with this, it stays where it is.
Stays pointing up.
So you're pressing on the back.
My jaw stands for sides we can see.
Exactly.
The other side, pressing the back, it's going that way.
These days, though, we can buy electronic artificial horizons, which are much better. They're generally always on, they don't take time to erect, they're less likely to topple, and they have lower power consumption. And here are a couple of examples. This is the LX 9050 with its horizon on, and you can put that on any of the pages in the 9000 series of products. And this is the LX S100, I think, with the artificial horizon option, which we can select by one of these buttons. And in both cases, they're quite easy to call up and use in cloud. Let's talk a little bit about the limitations of the instruments, starting with the attitude indicator. The attitude indicator presents us with quite a nice picture of what's going on, but certainly the older ones need to be erected before use. We need to turn them on and then wait till they're working before we can start turning. They're also pretty compelling when they're wrong. If you're actually wings level and you're looking at an attitude indicator which is giving you a 45-degree bank turn, it's quite hard to reject that picture. And then they've got a number of errors, precession errors, limitations on the angles they can go to. So we can cause them to topple and give erroneous indications. And lastly, they take quite a lot of power, and they might wind down if the battery is looking a bit low. The other instruments, the turn and slip, indicates rate of yaw rather than bank, so it's not really giving us what we want. There's a lot of lag to it. The airplane is going to move quite a lot ahead of the instrument. If we're pulling G, it's got significant errors. Its indication varies considerably with the true airspeed, and we have to be careful about how it is calibrated, whether a rate 1 turn indicated on the instrument is really a rate 1 turn. If it's been calibrated for a much faster aeroplane than a glider, it probably won't. So the ones in gliders need to have different springs in to make them read correctly. The airspeed indicator, again, has a lot of lag. So it doesn't really give us the correct indication of pitch that we are trying to use it for if we're flying with a turn and slip. It can misread if yaw is present. We've got the problem of the difference between indicated airspeed and true airspeed, and it's very susceptible to moisture or icing. The altimeter has indicator lag. It can be sticky. We've got an issue of how it's calibrated, and the static source can make a difference, particularly if it gets iced up. The compass is pretty useless unless we've got the wings level, and it suffers from both acceleration errors and turning errors. And whilst it is possible at least to compensate for those errors, it's quite complicated. So I think the strong advice is only use it if your wings level and unaccelerated. And then lastly, the variometer has lag and is susceptible to moisture and icing, and the yaw string is certainly susceptible to moisture and icing. So most of our instruments have quite significant limits. Let's have a look at navigation then. During the flying, the sort of skills that we're going to require are your ability to determine your present position by GPS or by dead reckoning, so that we can avoid solid-centered clouds and we can keep clear of controlled airspace. Now, my strong recommendation is that cross-country and cloud flying, we have a GPS, a moving map GPS. That's going to make life a lot easier. But the course requires us to be able to do a little bit of dead reckoning whilst we're flying. We need to be able to get to a waypoint, for example, a home airfield, much easier with a GPS. And we'll teach you something about performing a cloud break in a place from which a landing can be made. And that's quite a good exercise to practice your instrument flying skills. All of this is easy when not under pressure. It's much more difficult when hand flying in turbulent instrument meteorological conditions. And the preparation is pretty important. A map folded in the right place, if you're dead reckoning, a note of time and place of entry, the GPS set to the right waypoint, and a plan of action if it all goes wrong. Let's look a bit at communications. Starting with the radio. We have a cloud flying frequency, 130.535, and that's the glider cloud flying frequency. And the rule there is before entering cloud, we broadcast our call sign, our altitude, and our distance and bearing from a significant feature on a 500,000 chart. And that's so that if other people are thinking about doing the same thing, we can separate from them. When we leave cloud, again, we transmit the call sign and we say we're leaving cloud and what altitude we're at. If there are other gliders cloud flying in the vicinity, we report altitude from time to time. Now, actually, not very many people cloud fly. So it might be worth thinking about talking to an ATSU, an air traffic service unit, possibly getting a traffic service from them, possibly as well as making your calls on this frequency. If you've got the capacity, doing both is fine, and most modern radios have a dual watch facility so that you can be on both frequencies. But I would make a judgment as to, according to where I was, to help me decide that. And then we also have 121.5, distress and diversion, London Centre, and they can usually help you if you become uncertain of your position or think you might be about to violate controlled airspace. So they're worth talking to. If we're inadvertently caught out in cloud near base, near our home airfield, it may be best to stay with the home frequency, since there might not be anybody on 130.535, but everybody will be on the local airfield frequency. Now you can obtain information about conditions at the airfield, you can warn others of your imminent descent, and you can keep the base aware of your predicament in case you need assistance. If you enter controlled airspace inadvertently, if you've got the frequency called air traffic control, they can keep other traffic away from you. That's particularly important if you're in cloud and can't look out. Let's have a look at hazards and emergency procedures. So the first one we're going to think about is loss of control. So the basic stabilisation and recovery manoeuvre. What we do is we stabilise the glider, we regain straightened wings level flight, and then we think about what we're going to do next. How do we stabilise the glider? We hold the stick firmly central, we open the air brakes, and we allow the glider to stabilise. If we've got flaps, we want to have those flaps in a neutral setting. Once we've done that, if we've got an attitude reference, we can regain straightened wings level flight. If not, we've got to wait until we can see. But the glider will eventually come out of cloud. The key is to know your glider. How will it behave when you do this? When would you do that? Well, if your normal recovery techniques are not working, and well before your maximum manoeuvring speed is passed, that's the time to do it. Or if your airspeed is more than 20 knots above your target, then I'd do it then. If the sailplane is stalled, or if you're unable to maintain control due to instrument failure, including loss of pitot due to icing, especially if you were flying only by reference to the turn and slip, or if you feel excessively disoriented and unable to control the sailplane. So any of those conditions is enough to say, hold the stick in the middle, open the air brakes, and wait. But we're going to practice on recoveries from unusual attitudes. This mostly applies to flying on turn and slip. If you've got the wings level and your speed is increasing, then you raise the nose until the airspeed indicator needle is steady. You'll be at a higher than normal airspeed, then you can use small corrections to raise the nose to achieve the desired speed. Your risk is over controlling, which would lead to a stall. If your wings level and the speed is decreasing, then you lower the nose until the speed is steady, and you'll be lower than normal airspeed. And then again, use small corrections to lower the nose to achieve the desired speed. If you're banked and the speed is increasing, then the danger is a spiral dive. So we use the ailerons to level the wings and center the needle, allowing for the lag, and then we raise the nose until the speed is steady. Then we apply small corrections. If we're banked and the speed is decreasing, then we lower the speed lower the nose until the speed is steady. If necessary, until it's increasing slowly, then level the wings. So these things are all allowing for instrument lag. If we've got a working artificial horizon, it becomes much easier because we can basically adopt the attitude we know that we need. If in doubt, adopt the BGA recommended basic stabilisation manoeuvre. Let's talk a bit about ice. Cumulus clouds are full of water droplets, and above the freezing level they'll be supercooled below zero, and they like nothing more than a chance to turn into ice, and all they need is something to condense on. That can be your glider, so that would lead to very poor performance. Your aerofoil has changed, so your wings don't work very well. You have extra weight and a higher stall speed. You can lose instrumentation because your pitot is iced up. You have the potential of frozen controls, if not the main flying controls, almost very likely the air brakes. And you can have loss of vision through the canopy if your canopy is iced up. So avoid icing conditions if you can, but if you do get into them, leave them as soon as you can. Icing is very dangerous. A little bit of threat and error management, things that we might want to think about before we go into cloud. Are you fit? Are you dehydrated? Hungry? Probably not a good idea. Are the instruments on and erect? Do you have enough power? Is your battery about to run out? Is the datum attitude correct? Have you got the pitch set properly on the artificial horizon? Are you certain of your position and where airspace might be? Are you protected against distractions? Is the navigation system set up, the comms, the radio set with the frequencies you want, the cockpit without loose objects? And are you nice and relaxed and head down before entry? And when you're in cloud, do you avoid moving your head? Are you alert for icing? Do you know where your exit heading is? And do you have a plan if it all goes wrong? So some preparation is really important here. Let's talk a little bit about rules and common sense. So we'll start with the law. The air navigation order says it's not in controlled airspace, and we've got some operational regs. We need to think about the weather, how much cloud cover we've got, the safety altitude and terrain separation. You need to understand what a safety altitude is and how we make sure we are separate from the terrain. Whether we're expecting icing, what the wind is doing, how thick the cloud is going to be. What other people are going to do, what the limitations of our aircraft are, what the equipment we want, and what the preparation we need to do for entering cloud is. So it's basically have a plan. The BGA Operational Regulations say that we should wear a parachute in cloud. And it also says that no glider shall enter cloud within a radius of 5 nautical miles from a gliding site, except from at least 200 feet from below the lowest part of the cloud. So we can't go into cloud at the side of a cloud, but we can climb from underneath it so that other people can see what we're doing. And then as far as oxygen is concerned, the law says that if we're flying between flight level 100 and flight level 130 for more than 30 minutes, we should use oxygen, or any time we're above flight level 130. The BGA recommend for flights above 10,000 feet, we should use a supplementary oxygen supply. And if we get ill or feel ill in any way, we should make a descent. But actually, if you're going to go above about 8,000 feet, put the oxygen on much earlier, either on the ground or by 5,000 feet. There's a lot of evidence that that does some good. What's next? Well, you can expect to discuss the content of this part of the presentation during the flying session, so bone up on it. And in the next part of this presentation, we'll actually look at some of that flying that we'll be doing.